Hello again, everyone, and welcome back to our course in college algebra. Dr. Tom McNamara here, continuing our work with rational functions. In our last video, we saw that the graphs of rational functions have certain unusual features compared to the graphs of polynomial functions. Specifically, they have vertical and horizontal asymptotes. And in this video, we're going to look at finding the vertical asymptote. So this is everything you need to understand about vertical asymptotes of a rational function. And what we need to do is figure out all the values of x that make the denominator of our rational function equal to 0. So remember, a rational function is a fraction with a polynomial on top and a polynomial on the bottom. So you can have variables in the bottom. And you could have values of that variable that make the denominator 0. Those are going to be trouble because we can't divide by 0. Division by 0 is undefined. So that's the first thing we're going to need to find out whenever we have a rational function. What values of x make the denominator 0? We'll also need to do this. We'll need to check if anything cancels with something up top, because that can affect whether or not we have a vertical asymptote. And lastly, I'll just call this a check on behavior. So when you have a vertical asymptote, which we remember is a vertical line that the function cannot cross, the behavior of the function at that vertical asymptote is going to fit one of these four categories. Okay, these are just little partial graphs I'm drawing here. Okay, so the dashed line represents your vertical asymptote. So you could either be doing this, you could be doing this, both up or both down, okay? And you'll have to figure out which based on the specifics of your function. So let's go ahead and get into a quick example. Find the vertical asymptotes of each. Let's start out with this. F of x equals x minus 2 over x plus 1. Okay, so quick check. That is a rational function. You have a polynomial on top. It's a degree 1 polynomial. It's a linear polynomial, but it's still a polynomial. And you have a polynomial on the bottom. So we got a rational function. So we'll take that denominator, we'll set that equal to 0 and solve the resulting equation. Very quick one to do here. We get x equals -1. Okay? So the domain is -infinity to 1, union 1 to infinity. All right? So you're allowed to use any x value except, -1, sorry. Those should both be -1. Okay, -1 was the problem child. That's out of the domain. You can use anything else. Now, there's not going to be any cancellation with the top and the bottom. Remember, you can only cancel common factors. You cannot cancel terms. So you can't cancel out the x's here. X isn't a factor of the denominator. It's a term in the denominator. Okay, so we are going to have a vertical asymptote at x equals -1. Now the question becomes, what kind of behavior are we going to have at that vertical asymptote? So what I usually do is I just do a little check. I make myself a little sign chart. X equals -1 is the point that we're concerned with. I'll pick some test points on either side. Now here I kind of want to pick something that's a little close. let's take, I don't know, something a little bit less than -1. Let's say -1.1 for the bottom. And then -0.9. Okay, remember the negative numbers are ordered backwards, so -1.1 is actually less than -1. It's close to, but less than. Okay, so let's take these and plug them into the top. Now, I don't really care about the numerical value that I get, I care about the sign that I get. Okay, so if I plug in this value, top is negative, because we took a negative and we subtracted something, so the top is negative. The bottom is positive, okay? So the result is negative. If you take a negative, divide by a positive, you get a negative. Now here, -1.1. Once again, top is negative. You take a negative and subtract, you're going to get even more negative. But look at the denominator. -1.1 plus 1 is still negative. So the top is negative, the bottom is also negative. So the result of the division is a positive. The sign rules for division are the same as the sign rules for multiplication. Okay, I'm sure you already knew that. So this is telling me that on the left side, my graph is going to be going up. On the right side, my graph is going to be dropping down. That's how this function is going to behave at that vertical asymptote. Okay, and this is what I was talking about when I say check the behavior. What's your graph going to look like by that vertical asymptote? Because the vertical asymptote is going to be one of the defining features for this function's graph. Okay, so let's go and look at a few more examples here. We'll go through all of those steps for each of the rational functions I give you. We're going to, one, figure out where the vertical asymptotes are, check what the behavior is. Okay, so let's look at one like this. Let's do f of x equals 4x over x squared plus 3x minus 10. Okay, so we're going to take the denominator, set the denominator equal to 0, and solve that equation. Notice, when we're talking about finding the domain, we are completely ignoring the numerator. When we're talking about finding the vertical asymptotes / finding the domain. You can't divide by 0. Division by 0 is undefined. It's completely fine to have a 0 up top. Having a 0 down here is a problem. Okay, so back to the example. We're solving a quadratic equation. Main strategy would be to factor the quadratic equation, or factor the quadratic expression on this side of the equation, I guess I should say. So we factor it, we see that there are two solutions. X equals -5, x equals 2. Now there's no canceling in this case. I'll show you an example in just a sec where there is some canceling. Okay, but we have two vertical asymptotes, and we have 2 points that are excluded from the domain. The domain is -infinity to -5, -5 to 2, and 2 to infinity, if we're going to use interval notation. Okay, so it's like we took the entire real number line and we plucked out -5 and 2. Those are 2 points we can't use. So the vertical asymptotes, I'm usually just going to abbreviate that VA on all of our videos. The vertical asymptotes are x equals -5, x equals 2. Once again, I'm interested in the behavior of my function at these vertical asymptotes. So I'll make a little sign chart, very similar to what I did just a second ago. Okay, I'm I'm wanting to pick stuff that's kind of really close to -5, 1 less, 1 greater, and really close to 2, 1 less, 1 greater. So I have this little weird thing happening in the middle there. That's okay. All right. So once again, I do not care about the numerical value of the function at these inputs. What I care about is the sign, because I'm trying to determine, is this thing going up or is this thing going down when we come to our vertical asymptote. So let me take -5.1. I would really encourage you to put it in here. Negative, negative, negative. You got 3 negatives. So the result is negative. That means the graph is going to be dropping. There. Okay, -4.9. Positive, negative, negative. 2 negatives. So at -4.9, I'm positive, going up. Okay, remember, you could go up, down. It could be reversed. You could go up on both sides, or you could go down on both sides. You have to do this chart to figure it out. Okay. So, let's plug in 1.9. Positive, negative, positive. 1 negative means we have a negative. Graph is going to be dropping on this side of the vertical asymptote at x equals 2. Lastly, 2.1. Positive, positive, positive. Everything is positive, so result is positive. Our graph is going to be going up over there. And I didn't do this for the last one. There are a couple more tools that we're going to need, but I can really quickly get you a graph of this rational function. Okay, very quick graph, and very accurate too, I might add. I just want you to see how all the components fit together in this example. All right, so let me use a nice piece of orange chalk. 1, 2, 3, 4, 5. Vertical asymptote at x equals 5. So when you're drawing your graph, we're going to draw a dotted line there at x equals 5. Vertical asymptote at x equals 2. Once again, draw a dashed vertical line there. Okay? So what's happening around here? Well, the graph, as we can see, is going to plunge down on this side. It's going to rocket up on that side. I'll show you later how I know that the graph is going to flatten out towards y equals 0 here, but for right now, just take my word for it. This goes through the origin, by the way. If you plug in 0, you get 0 out. And the graph is going to plunge down right here. Look at what we're seeing. Plunge down. Okay, let's connect like that. And over here, up. Okay, so knowing those vertical asymptotes gets me basically almost all the information I need about the graph. I just need to figure out how it flattens out, which we'll discuss later. Okay, but the vertical asymptotes are a big defining feature for a graph like this. And this sign chart that we're doing right here is helping us figure out, do we go down, do we go up? Well, test, check. Put in a number that's close to your vertical asymptote. Are you getting a negative or are you getting a positive? Okay, 2 more examples. So in all these examples, we want to find the vertical asymptotes for the function. Okay, let's do this one. F of x equals 1 over x squared plus 5. So we are going to solve an equation. Okay, we always start the process the same way. When you got a rational function, our big concern is what makes that denominator 0? What x values make that denominator 0? Because those could be vertical asymptotes. So we're going to solve an equation. We set the denominator equal to 0, we solve it. Now in this case, we have no real solution. Okay, so basically, what is this saying? Well, if my x value is a solution to this equation, I have to take my x value and square it, and add 5 and get 0. So that means after I take my x value and square it, I should have negative 5. Now this is a problem. Okay, take a positive number. You take a positive number and square it, it's positive times positive, so you get a positive. All right, so x can't be positive. All right, take a negative number. If I take a negative number and I square it, that would be a negative number times itself. A negative number times a negative number, which would be a positive number. So x can't be negative. And of course 0 won't work. 0 squared is 0. So this has no real number solution. Which implies this rational function has no vertical asymptote. Okay, this graph will not have a vertical asymptote. Okay, you get vertical asymptotes where the denominator is 0, and that denominator is not 0 for any real number. Okay, one more. All right. X squared minus 4 over x plus 2. So rational function, right? Polynomial up top, polynomial downstairs. Okay, so we always start out by doing this. So x equals negative 2 is a problem. That is excluded from our domain. Now here's the thing. I want you to notice, this is an example, we haven't seen one like this before. My numerator factors. It factors into x plus 2 times x minus 2. Okay? If you multiply out, you'll see, right? X squared minus 2x plus 2x, those would cancel. Minus 4. Okay, that's called difference of two squares factoring. Okay, so my numerator factors. And my denominator, notice that factor coincides with this one right here. So those can be canceled. This thing simplifies to x minus 2. Okay? So because of that canceling, I will not have a vertical asymptote. I'm going to talk more about this in a later video, but it'll turn out this is a situation where the graph has a hole at a certain x value rather than a vertical asymptote. So just watch out for this. Doesn't come up too often, okay, but try to see if there are any common factors. If there are, cancel them. If your factor associated with a problem value in the domain goes away, you don't get a vertical asymptote. Okay, so 2 examples of rational functions where we didn't get vertical asymptotes. Most of the time we're going to get vertical asymptotes with these rational functions, but not always, so be careful.